Section: Introduction. In this section, we discuss the emergence of foundation models, which have shown impressive capabilities by scaling both the model and data significantly. For instance, OpenAI's Sora not only creates high-quality and surreal videos but has also reignited interest in world models. We believe that scaling video generation models could lead to the development of general-purpose simulators for the physical world. These simulators are gaining attention in fields like robotics and autonomous driving due to their ability to produce realistic data and accurate simulations. However, it remains uncertain whether video generation can uncover fundamental physical laws just by observing videos, as Sora does. Our goal is to systematically study the importance and limitations of scaling in discovering these laws. It is difficult to determine if a video model has genuinely learned a law or is simply memorizing data, as we cannot access the model's internal knowledge. We can only infer its understanding by analyzing its predictions on new scenarios, which reflects its generalization ability. To evaluate this, we propose a categorization based on the relationship between training and testing data. In distribution, generalization assumes that training and testing data are similar, while out-of-distribution generalization refers to the model's performance on testing data that differs from the training data. Human-level reasoning can easily predict outcomes in new situations without having seen them before. We also look at a specific type of out-of-distribution generalization called combinatorial generalization, which tests if a model can creatively combine two different concepts, a key trait for advancing towards artificial general intelligence. Real-world videos often feature complex objects and motions, making evaluation challenging. To address this, we focus on classical mechanics and create a 2D simulator using simple geometric shapes. Each video shows the motion or collision of these shapes, governed by basic physical laws. This setup allows us to generate large datasets to enhance video generation models. We also developed a tool to extract internal states of objects from the generated videos, enabling us to create quantitative metrics for discovering physical laws. We begin by examining how scaling video generation models impacts both in distribution and out-of-distribution generalization. We simulate three fundamental physical laws: the uniform motion of a ball, perfectly elastic collisions between two balls, and parabolic motion. We scale our dataset from 30,000 to 3 million examples and increase the model's parameters from 22 million to 310 million. We consistently find that the model achieves nearly perfect in distribution generalization across all tasks. However, the out-of-distribution generalization error does not improve with larger data and model size, highlighting the limitations of scaling in handling out-of-distribution data. For combinatorial generalization, we create an environment with multiple objects in free fall and collisions. We select 4 objects from a set of 8 to generate videos, resulting in 70 possible combinations. We use 60 for training and 10 for testing, varying the training data from 600,000 to 6 million examples. We manually label generated test samples as abnormal if they appear physically implausible. Our results show that scaling the data significantly reduces the percentage of abnormal cases from 67% to 10%, indicating that scaling is crucial for improving combinatorial generalization. Our analysis reveals 2 interesting aspects of the generalization mechanism in video generation models. First, these models can be influenced by misleading examples from the training set, causing them to generalize based on specific cases. For example, if a model trained on high-speed ball motion is given flipped videos, it might incorrectly generate a low-speed ball reversing direction, which is not physically accurate. Second, we investigate how different data attributes compete during generalization. For instance, if training data includes red balls and blue squares, the model might prioritize color over shape, transforming a red square into a ball after the initial frames. Our analysis shows a hierarchy of prioritization: color, size, velocity, and then shape. This could explain why current video generation models often struggle with maintaining object consistency. We hope our findings will provide valuable insights for future research in video generation and the development of world models. Section Summary. In this section, we explore the capabilities and limitations of scaling video generation models in discovering physical laws, focusing on their generalization abilities through systematic evaluation. Our findings indicate that while scaling improves in distribution generalization, it does not enhance out-of-distribution performance, and we identify biases in the model's learning processes that affect their ability to maintain object consistency. Section: Discovering Physics Laws with Video Generation. In this section, we aim to set up a framework and define the idea of discovering physical laws through video generation. In classical physics, laws are expressed as mathematical equations that predict future states based on initial conditions. When we observe videos, each frame captures a moment in time, and predicting physical laws means generating future frames based on past ones. We consider a physical process with several hidden variables, which represent different physical parameters like velocity or position. According to classical mechanics, these variables change over time according to a differential equation. In simpler terms, if we look at the time between two frames as a small interval, we can express the change in these variables as their current state plus a small adjustment based on their current values. We define a rendering function that transforms the state of the world into an image. For a video made up of several frames, we require that the hidden variables evolve according to our earlier equation and that each frame corresponds to the state represented by those variables. We train a video generation model that captures its understanding of the frames. We can then predict future frames based on the initial ones, and we measure how well our predictions align with reality using a physical coherence loss function. This loss function helps us evaluate whether our model accurately discovers and simulates physical laws. For video generation, we use variational autoencoder, VAE, and DIT architectures. The VAE compresses videos into latent representations over both space and time, while the DIT focuses on the denoising process. This combination shows strong scalability and produces high-quality videos. We utilize a specific type of VAE to project videos into a latent space, ensuring it is pre-trained on high-quality data to maintain strong modeling of both appearance and motion. Once we have the compressed representation, we convert it into a sequence of spacetime patches, treating them as tokens for a transformer model. We apply self-attention across the entire sequence without separating spatial and temporal aspects. We also create a binary mask to indicate which frames are used as input conditions for the model. To verify if our learned model has discovered the correct physical laws, we need to assess its predictions. A valid physical law should accurately describe how objects behave in the natural world. Our model should be able to produce reasonable predictions in various scenarios, demonstrating its ability to generalize. We categorize generalization into three types. 1. In distribution generalization, where both training and testing data come from the same distribution. 2. Out-of-distribution generalization, where the model can apply learned laws to new, unseen scenarios. 3. Combinatorial generalization, where the model combines known concepts in novel ways, even if it hasn't seen every possible combination before. This categorization helps us evaluate how well our model learns and applies physical laws. Section Summary. In this section, we establish a framework for discovering physical laws through video generation, where we predict future frames based on past states using latent variables that evolve according to classical mechanics. We utilize a variational autoencoder and a diffusion model to compress and generate videos, and we evaluate the model's ability to learn physical laws through various generalization categories, including in-distribution, out-of-distribution, and combinatorial generalization. Section: In-distribution and out-of-distribution generalization. In this section, we explore the relationship between in-distribution, ID, and out-of-distribution, OOD, generalization and how it relates to scaling models and data. We concentrate on deterministic tasks defined by basic kinematic equations, which help us clearly identify ID and OOD scenarios and evaluate errors quantitatively. We examine three fundamental physical scenarios. 1. Uniform linear motion. A colored ball moves horizontally at a constant speed, demonstrating the law of inertia. 2. Perfectly elastic collision. Two balls of different sizes and speeds collide while moving towards each other, illustrating the conservation of energy and momentum. 3. Parabolic motion. A ball with an initial horizontal speed falls under the influence of gravity, representing Newton's second law of motion. Each motion is determined by its starting conditions. To generate training data, we use Box 2D to simulate various kinematic states and create videos, each with 2 to 4 degrees of freedom, such as the ball's initial velocity and mass. We define an in-distribution range for each degree of freedom and produce training datasets of 30,000, 300,000, and 3 million videos by sampling from a high-dimensional grid within these ranges. All balls have the same density, so we derive their mass from their size, and gravitational acceleration remains constant during parabolic motion. Initial positions of the balls are randomly set within the visible area. For testing, we evaluate our trained model using both ID and OOD data. For ID evaluation, we sample from the same grid used in training, ensuring no specific data point overlaps with the training set. OOD evaluation videos are created with initial values for radius and velocity that fall outside the training range, with various OOD settings possible. We train models of different sizes from scratch for each scenario, ensuring that results are not affected by uncontrolled pre-training data. We provide the first 3 frames as input, which is enough to infer the ball's velocities and predict future frames. We train a diffusion model for 100,000 steps using 32 NVIDIA A100 GPUs with a batch size of 256, which is sufficient for convergence. We keep the pre-trained variational autoencoder, VAE, fixed. Each video consists of 32 frames at a resolution of 128 by 128 pixels, and we also tested a higher resolution of 256 by 256, which resulted in similar generalization errors but slowed down training. To evaluate our models, we find that they generate balls with consistent shapes. We use a heuristic algorithm to determine the center positions of the balls in the generated videos, distinguishing them by color. We exclude frames where parts of a ball are out of view to ensure accuracy. For collision scenarios, we only consider frames after the collision. We calculate the velocity of each ball by differentiating their positions. The error for a video is defined as the average difference between the computed velocity and the ground truth velocity from the simulator. We also calculate the error between the ground truth velocity and the parsed values from the ground truth video, which represents the system error and sets a minimum error threshold for our model. Our main results show that increasing the model size or the amount of training data consistently reduces velocity errors for ID generalization across all tasks. For instance, the smaller model with 30,000 data points has a velocity error of 0.022, while the larger model with 3 million data points achieves an error of 0.012, close to the ground truth error of 0.010. However, for OOD predictions, the errors are significantly higher, and scaling the training data or model size does not effectively reduce these errors. The variation in OOD velocity errors is quite random as we change data or model sizes. We trained a larger model on the uniform motion dataset but saw no improvement in OOD generalization, leading us to conclude that scaling does not enhance reasoning in OOD scenarios. The stark contrast between ID and OOD results encourages us to further investigate the generalization mechanisms in video generation. Section Summary. In this section, we investigate the relationship between in-distribution ID and out-of-distribution OOD generalization in models trained on deterministic kinematic tasks, finding that while increasing model size and training data consistently reduces ID errors, it has little to no effect on OOD errors, which remain significantly higher and more variable. This stark contrast highlights the limitations of scaling and improving reasoning for OOD scenarios, prompting further exploration of the generalization mechanisms in video generation. Section: Combinatorial Generalization. In this section, we evaluate how well diffusion-based video models can combine known information to predict new scenarios, a skill known as combinatorial generalization. We chose the fire simulator for our tests, which is a 2D environment where various objects fall and collide, creating complex physical interactions. This simulator includes different object types like balls, jars, and bars, allowing for interactions such as collisions and rotations. Despite the complexity, the physical laws governing these interactions are clear, enabling our model to learn and predict new situations. We considered 8 object types, including 2 dynamic gray balls and several fixed and dynamic objects. Each task involved 1 red ball and 4 randomly selected objects, leading to 70 unique combinations. We generated 100,000 videos with random sizes and positions for these objects to explore the model's combinatorial abilities. We structured our training data at 3 levels: a minimal set of 6 templates with 600,000 videos, and larger sets with 30 and 60 templates, covering nearly all possible combinations. The minimal set challenges the model's ability to generalize. For testing, we set aside some videos from each training template for in-template evaluation and reserved 10 unused templates for out-of-template evaluation to see how well the model generalizes to new combinations. We used the first frame of the video as a starting point for generation. Smaller models struggled with complexity, so we focused on larger models like DIT-B and DIT-XL, training them extensively to ensure they learned effectively. To evaluate the generated videos, we used several metrics, including Frechet video distance, SSIM, PSNR, and LPIPS, along with human assessments of how many videos violated physical laws. Our main findings indicate that higher resolution, more training iterations, and larger models are necessary for success due to the task's complexity. We began our analysis with the largest model, DIT-XL, and found that increasing the number of templates from 6 to 60 improved all evaluation metrics, significantly reducing the rate of abnormal videos from 67% to 10%. However, the model trained on 6 templates performed best in template tests due to more frequent exposure to those examples. We also tested a DIT-B model on the full set of 60 templates, which resulted in a higher abnormal rate of 24%. These results highlight the importance of both model capacity and the diversity of combinations for effective combinatorial generalization. This suggests that scaling laws for video generation should prioritize increasing the variety of combinations rather than just increasing data volume. Visualizations of our model's video generation can be found in the accompanying figures. Section Summary. In this section, we evaluate the combinatorial generalization abilities of diffusion-based video models using the Fire simulator, which allows for complex physical interactions among various object types. Our findings indicate that increasing the diversity of training templates significantly improves the model's performance in predicting unseen scenarios, highlighting the importance of both model capacity and the coverage of combination spaces for effective video generation. Section: Deeper Analysis. In this section, we aim to explore how a video generation model generalizes through carefully designed experiments. Our goal is to uncover patterns in combinatorial generalization that could help us better utilize these models. We begin by examining generalization through interpolation and extrapolation. The model's ability to generalize stems from how well it can interpolate and extrapolate. To investigate this, we create datasets that intentionally omit certain latent values, such as velocity. After training, we evaluate the model's predictions in both familiar and unfamiliar scenarios, focusing on uniform motion and collision events. For uniform motion, we prepare several training sets that lack a specific range of velocities, each containing 200,000 videos for consistency. We observe that when there is a significant gap in the training data, the model tends to generate videos with either very high or very low velocities, even when the initial frames show mid-range velocities. We find that the model's accuracy in out-of-distribution (OOD) scenarios is closely linked to the size of this gap. When we reduce the gap, the model performs better in interpolating most OOD data. Additionally, when we reintroduce a portion of the missing velocity range without adding more data, the model shows improved interpolation skills. Collision scenarios are more complex due to multiple variables, requiring the model to learn a two-dimensional nonlinear function. We exclude certain initial velocity regions for two balls and then measure the prediction error after collisions. We sample various parameters to generate multiple video cases and calculate the average error. We notice an intriguing pattern. The model performs well on odd velocity combinations that fall within the training set's convex hull, but it struggles with those outside this area. Next, we consider whether video generation models rely on memorization rather than true understanding, similar to findings in large language models, LLMs. We investigate if these models simply reproduce training data instead of grasping the underlying physical principles, which could hinder their ability to generalize to new data. To illustrate this, we train our model on uniform motion videos with specific velocity ranges, using the first 3 frames as input. We create 2 training sets, one with balls moving only in one direction and another that includes movement in both directions. During evaluation, we focus on low-speed balls that were not part of the training data. We find that the first model generates videos with only positive velocities, while the second model occasionally produces videos with negative velocities. This suggests that the model is influenced by misleading examples in the training data, relying more on memorization and imitation rather than abstracting universal rules for generalization. Section Summary. In this section, we investigate the generalization mechanisms of a video generation model through systematic experiments, focusing on its interpolation and extrapolation capabilities. Our findings reveal that the model tends to rely on memorization rather than understanding underlying physical laws, which limits its ability to generalize to unseen data, particularly in scenarios involving uniform motion and collisions. Section. How does diffusion model retrieve data? In this section, we explore how a video model matches cases by finding similar training examples for a given test input. We focus on uniform linear motion and compare 4 attributes: color, shape, size, and velocity, looking at them in pairs. Our goal is to see which attributes the model prefers for case matching. Each attribute has 2 separate sets of values, and for each pair, we create 4 combinations. We use 2 combinations for training and the other 2 for testing. For instance, when comparing color and shape, we train with videos of red balls and blue squares that have the same size and velocity. During testing, a blue ball changes into a square, and a red square turns into a ball. We found no exceptions in 1,400 test cases, indicating that the model favors color over shape. This trend also appears when comparing size with shape and velocity with shape, suggesting that shape is the least important attribute. This preference may explain why current video generation models often struggle to maintain shape. When we look at the combination of velocity and size, the model performs well, keeping the initial size and velocity for most test cases. However, it shows a slight preference for size, especially with extreme values. In the case of color and size, the model can often combine these attributes effectively. For color and velocity, we trained with fast blue balls and slow red balls. During testing, low-speed blue balls appeared much faster than expected, and no balls changed color, reinforcing that color is prioritized over velocity. Overall, we conclude that the order of importance is color, followed by size, then velocity, and lastly shape. Next, we investigate how complex combinatorial generalization occurs. We found that increasing data coverage can enhance this generalization. We identify 3 fundamental patterns through our experiments. 1. Attribute composition. Certain pairs like velocity and size or color and size show some combinatorial generalization. 2. Spatial composition. Our training data includes 2 types of physical events, such as a blue square moving while a red ball stays still, and a red ball bouncing off a wall while the blue square remains stationary. The model can generate scenarios where both objects move simultaneously. 3. Temporal combination. When training data includes different physical events, like balls colliding and bouncing, the model learns to combine these events over time. During evaluation, it can predict the outcome of a collision near a wall and determine the rebound of a ball. With these patterns, our video generation model can recognize basic physical events in the training set and combine them across attributes, time, and space to create videos that depict complex sequences of physical events. Section Summary. In this section, we investigate how a video model performs case matching by comparing attributes like color, shape, size, and velocity, revealing that the model prioritizes color over shape in its retrieval process. We also identify three fundamental combinatorial patterns: attribute composition, spatial composition, and temporal combination, that enable the model to generate complex video scenarios by combining learned physical events. Section: Is video sufficient for complete physics modeling? In this section, we explore whether video alone is enough for complete physics modeling. For a video generation model to serve as a world model, it must provide enough visual information for accurate physics representation. Our experiments show that visual ambiguity can lead to major errors in detailed physics modeling. For instance, when trying to determine if a ball can fit through a narrow gap, the size difference at the pixel level makes it hard to tell just from what we see, resulting in visually convincing but incorrect conclusions. Similarly, if there is ambiguity in a ball's horizontal position next to a block, it can lead to different interpretations. These results indicate that depending solely on visual data may not be sufficient for precise physics modeling. Regarding related works, we note that open-set video generation typically relies on diffusion or auto-regressive models. These often need a pre-trained image or video variational autoencoder, VAE, to enhance computational efficiency. Some methods utilize pre-trained text-to-image models for generating videos with little or no prior examples. Additionally, image-to-video generation shows that video quality significantly improves when based on an image. The diffusion transformer has shown better scaling than UNet for text-to-image generation, and Sora uses this architecture to work directly with video and image data. Our model is inspired by Sora's design and aligns with image-to-video generation, using images for conditioning rather than text prompts. World models aim to accurately predict how environments change after actions are taken. Traditionally, they worked in abstract spaces for reinforcement learning, aiding in planning and policy learning through virtual interactions. With advancements in generative models, world models can now directly utilize visual observations through a framework of conditioned video generation. For example, in autonomous driving, the condition is the driver's actions, while in robotic models, it often involves control signals. Genie, on the other hand, learns conditions from video games without supervision. In our approach to discovering physical laws, we do not need specific actions or conditions at each step, as the physical event is determined by the underlying laws once we set an initial state. For more related works, see the appendix.